Welcome to the 8th session for the Flipped Classroom for AP Calculus. Today we're going to be discussing limits at infinity. Some simple notation. We would say the limit of f of x as x approaches infinity, or the limit of f of x as x approaches negative infinity. Example would be if we take the limit of 1 over x as x approaches infinity, that limit would be 0 because as x gets very large on the x-axis, 1 over x gets very, very small. If you graph this, you'll see that the curve gets very close to the x-axis but never touches it. This would mean that there's a horizontal asymptote at y equals 0, another name for the x-axis. Another example would be using our same function 1 over x. As x approaches negative infinity, that limit would still be equal to 0. Check this by graphing it and looking at the y values as you move from x equals 0 to far out on the left side of the x-axis. The values of that curve would still approach y equals 0, which would be another name for the x-axis. Properties of limits at infinity. All of the rules that we discussed in the previous section, such as the sum rule, the quotient rule, the power rule, the product rule, they all apply to infinite limits. So the limit of f of x plus g of x as x approaches infinity is equal to the limit of f of x plus the limit of g of x as x approaches infinity. Limits of rational functions. Remember, rational functions are two functions divided by one another. Three cases need to be considered. Case 1, 5x squared plus 8x minus 3 divided by the quantity 3x squared plus 2. Notice that the highest power of x in the numerator and the highest power of x in the denominator are the same. This defines case 1. In this case, that power would be 2. The procedure is this. Divide both top and bottom by the highest power of x, or x squared. The next slide will show you the details of what you get when you do that. Hopefully you can read this. We have the limit as x approaches infinity. Here I've divided the top by x squared, the bottom by x squared. The next thing we do is we do some simplification. We get 5 plus 8 over x minus 3 over x squared, all of that over 3 plus 2 over x squared. Then we take the limit. Well, the limit of a constant is the constant, that's 5. The limit of 8 over x, remember, it would have to be 0. And the limit of 3 over x squared would have to be 0. So the top equals 5. On the bottom, the limit of 3 would be a constant, which is 3. And the limit of 2 over x squared would be just 0. So our final answer is 5 over 3. Okay, you're actually getting an answer on this because in the cases where the numerator of the top and the numerator of the bottom, the highest power, are the same, you will always get an answer for the limit, a constant. This would also mean that there is a horizontal asymptote to this graph at y equals 5/3. Case 2. Limit as x approaches infinity of, let's say, the function 11x plus 2, that quantity, divided by 2x cubed minus 1. Here, the highest power of x in the denominator is greater than the highest power in the numerator. That's what defines case 2. The strategy is to divide the top and bottom by that highest power of x in the denominator, x cubed. The next slide shows the details. Limit of x approaches 0 of 11x plus 2 over 2x cubed minus 1. Divide top and bottom by x cubed. Okay, so you get 11x over x cubed plus 2 over x cubed all over 2x cubed over x cubed minus 1 over x cubed. Take the limit. Okay, so I did some simplification. I get 11 over x squared plus 2 over x cubed over 2 minus 1 over x cubed. Well, the limit of 11 over x squared would be 0. The limit of 2 over x cubed would be 0. The limit of 2 is a constant, that would just be 2. And the limit of 1 over x cubed is 0. So the answer comes out to be 0. So the rule here is when the highest power of x in the denominator is greater than the highest power of x in the numerator, the limit at infinity or negative infinity would be 0. Okay? But you still need to be able to show the algebra of how you get that. And that's what I've done here. The next case, case 3, find the limit as x approaches, let's say, negative infinity this time, of 2x squared minus 3 over 7x plus 4. That's not a negative sign in front of that. That's just a bullet marking the problem. All right, so we're going to divide the top and bottom by the highest power of x in the denominator. That would just be x. So in this case, you notice that the highest power of x in the numerator is actually greater than the highest power of x in the denominator, because that's x squared, whereas the bottom has x. This would be what defines a case 3 problem. And here's the details. Okay, again, divide top and bottom by x, not x cubed, which is in the numerator. It's always the highest power in the denominator. Okay, so I get 2x squared over x minus 3 over x all over 7x over x minus 4 over x. Okay, so now we do some simplification. I get 2x minus 3x all over 7 minus 4 over x. Take the limit. Well, the limit of 2x as x approaches negative infinity is simply negative infinity. You cannot get bigger or really smaller than negative infinity, so therefore when I put negative infinity in for x, I just get negative infinity. The limit of 3 over x would be 0. The limit of 7, a constant, would be just 7. And the limit of 4 over x would be 0. So the answer, you can see, is negative infinity. Okay, so this limit really is what we would say it decreases without bound, or it is approaches negative infinity, the limit. Okay? Those are the 3 cases for taking limits of rational functions. Practice problems we want to work on would be on page 122, 123, 1 through 24. 21 through 24 are a type of problem that I will need to go over with you in class. See you then. Bye.